For millennia, it was the definition of impossible magic, Cresapia, turning base metals into pure gold.
The alchemist's dream.
Exactly. And alchemists, they failed for centuries. But our sources for this deep dive suggest this ancient quest has finally been solved, not with magic, but with high-tech nuclear engineering.
That's really the core insight, isn't it? We're looking at a paper that shows how fusion energy plants, which are designed for clean electricity, are also sort of perfectly engineered to produce massive amounts of stable gold.
So we're taking mercury, a specific isotope,
Mm-hmm.
and turning it directly into text, which is gold. But, why now? Why couldn't we just do this years ago with, a standard fission reactor?
It all comes down to the physics of it, the energy of the neutrons. Fission neutrons are just they're too slow, too low energy. They only get up to about 0.75 MeV.
Not enough punch.
Not nearly enough. To crack that mercury nucleus, you need a high-energy sledgehammer.
And that's where DT fusion comes in.
Precisely. And this is where it gets really interesting. Deuterium-tritium fusion, it generates these incredibly fast neutrons. We're talking 14.1 MeV.
Wow, okay. That's a huge jump.
It's a game changer because the reaction we need, this N-to-N reaction, has an energy threshold around 9 MeV. So a 14.1 MeV neutron slams into the mercury-198 atom, kicks out 2 neutrons, and what's left behind is gold-197.
So those fusion neutrons are the key. But is this just a nice byproduct, or is it actually part of the design?
It's mandatory. This is the crucial part. Fusion reactors have to breed their own tritium fuel to be sustainable. To do that, to get your tritium breeding ratio above 1, you must use something to multiply the neutrons.
And that something is the mercury.
Exactly. By using mercury-198 as the neutron multiplier, the system creates the extra neutrons it needs for fuel, and it creates gold in the process. The transmutation is an essential function of the reactor.
It's profound systems optimization. Designing it so a required function also creates this incredible revenue stream.
It really is. It takes optimizing the physics, the engineering, and the economics all at the same time.
Optimizing these kinds of complex integrated systems is a huge challenge. And actually, that reminds me, this deep dive is brought to you by Embersilk.
Mm-hmm.
If you're trying to solve complex technical problems and turn them into scalable business solutions, Embersilk specializes in AI training, automation, and software development. They help businesses figure out where AI and advanced software agents can make the biggest impact. So for serious AI needs, check them out at embersilk.com. So, okay, let's talk about the economic scale here.
Right.
The paper says over 2 metric tons of gold per year per gigawatt. If fusion takes off, won't we just flood the market and crash the price of gold?
That is the critical question, yeah. But the global gold market is huge. Miners pull about 3,300 tons out of the ground every single year.
So there's a lot of room before we saturate it.
A lot of room. Fusion can help subsidize the deployment of terawatts of clean power before that becomes an issue. For a single plant, the gold revenue could literally double its entire annual value. It pushes the investment case into the billions.
It completely changes the investment picture for clean energy. So what are the main hurdles to making this real?
The paper points to 2 main things. First, separating out that specific isotope from natural mercury. And second, just material compatibility inside the reactor.
Are these solvable?
Oh, absolutely. They're framed as engineering challenges. The cost estimates for the isotope separation are actually really favorable. We're talking dollars per kilogram, not thousands.
And where does all this mercury come from? We're not about to start a new dirty mercury mining industry, are we?
No, far from it. It's actually the opposite. We have massive stockpiles of mercury already, tens of thousands of tons sitting in government and industrial waste sites in the US and the EU.
So we'd be cleaning up a toxic material.
And permanently transmuting it into a stable, valuable asset. It is literally resource cleanup built right into energy production.
And it's not just gold, is it? The potential here is much broader.
Much broader. This is the beginning of industrial element synthesis. You could apply the same principles to make palladium from silver or maybe osmium from rhenium. We are starting to learn how to engineer resource abundance.
So what began as this ancient, magical quest for gold has been transformed into a 21st century engineered solution. Fusion is becoming more than a power source. It's a multi-product industrial platform.
It's solving energy and resource challenges at the same time. The ability to purposefully transform elements like this, it points to a future that's defined not by scarcity, but by what we can create.
If you enjoyed this deep dive, please subscribe to the show. Hey, leave us a 5-star review if you can. It really does help get the word out. Thanks for tuning in.